Okay, so now that we understand the Landauer approach to current transport, let's apply that approach and understand current flow, first of all in small devices, but then in large bulk semiconductors. So our goals here, first of all, are to understand that some very interesting feature of transport that occurs in small nanostructures. This is called quantized conductance. We won't make much use of this in the remainder of the course, but it is a really interesting and important concept that you should know about. The second goal then will be to use this approach to derive a current equation for a large bulk semiconductor. Now, traditional semiconductor physics is based on current equations that work in the bulk. So this is where our focus is going to be for the remainder of the course after this lecture. So just to remind you, we have this approach to current flow in a small nano device. We describe it by this Landauer equation. Key parameters are transmission, channels, and Fermi window. All right. Now, we are going to restrict our attention in these discussions to the cases where we apply small voltages between the contacts. This will be called linear transport. If we have a bulk semiconductor, we'll be applying small electric fields. Now, things can become much more complicated if we go to high electric fields. But we'll find out in the next lecture that we can modify the effects for small electric fields or small biases and make the results work reasonably well for high electric fields as well. So we'll see how that plays out later. But for now, the focus is on small applied voltages, small electric fields. So let's begin with our expression for the current. And what's important here is this Fermi window. And we're going to approximate that Fermi window for a small voltage difference across the two contacts, assuming, again, that the temperatures of the two contacts are the same. So the Fermi function of contact 1 will be given by our Fermi function with Fermi level 1. And since we're near equilibrium, this is going to be essentially the equilibrium Fermi level. Both Fermi level in contact 1 and the Fermi level in contact 2 are very close together, close to where they were in equilibrium. So to find Fermi level 2, we take Fermi function 1 and we expand it in a Taylor series expansion. So we'll differentiate it with respect to the Fermi level, and then we'll multiply by the difference in Fermi levels between the two contacts. Okay. Well, notice I can make a slight change here. If we look at our Fermi function, if I differentiate with respect to Fermi energy, that's exactly the same as differentiating with respect to energy, except for a minus sign. So it'll be convenient to express this as minus dF dE instead of with respect to the Fermi level. All right, now I just subtract F1 minus F2, and you can see that the difference between those two is proportional to the difference in the Fermi levels between the two contacts. Now, why are the Fermi levels in the two contacts different? It's because I've applied a voltage to contact 2. Positive voltage lowers the Fermi energy in contact 2, so that difference is just minus Q times the voltage applied to contact 2. So the bottom line then is that F1 minus F2 can be expressed by this Taylor series expansion. There is a term minus dF naught dE that comes from differentiating the Fermi function, and then Q times the voltage that is applied to contact 2. This is the small voltage approximation that we're going to make for our Fermi window, F1 minus F2. Okay, so if we look at that just a little bit more, here's a plot of our Fermi function. The Fermi window is proportional to the minus the derivative. You can see that the slope is negative around the Fermi energy. So minus the derivative is going to give me some quantity that's positive centered around the Fermi energy. If you look at that, the area under that curve, it's an exercise that it's worth having a try at. You can show that the area under that curve is 1. The width is a few kT. So as we cool a device and make this width narrower and narrower, this Fermi window is going to have the properties of a delta function. That makes life really easy because it's simple to integrate delta functions. Okay, well, with that background, we're ready now to compute the current when we apply a small voltage to contact 2, beginning with our Landauer expression. So we'll simply replace F1 minus F2 with our Taylor series expansion. You can see that F1 minus F2 is proportional to the voltage that we apply. So we'll find that the current is proportional to the voltage that we apply. The constant of proportionality will be this capital G, the conductance of this nano device. So basically, we've shown that we're going to get Ohm's law. So the result is, under small biases, current is conductance times voltage. The conductance is given by the expressions that we've developed here: transmission, number of channels, minus dF naught dE, which came from the Taylor series expansion that was used to approximate the Fermi window. All right, so we've got an expression for the current. Let's take a look at this current at t equals 0. Remember, at t equals 0, this derivative of the Fermi function acts like a delta function at the Fermi energy. That means when I do this integral, we just pull out the transmission and the number of mean free paths at the Fermi energy. And we get a very simple expression for the conductance. It's 2q squared over h times the transmission for electrons with an energy at the Fermi energy times the number of channels at the Fermi energy. Okay, now we can do this in 1D, 2D, and 3D. If I have a large 3D semiconductor, 2D semiconductor, where electrons are flowing in a two-dimensional sheet, then the number of channels is going to be proportional to the width of the sheet. The wider it is, that's like making resistors in parallel, I'll have more channels. But if the width is very small, I'll get down to a point where the number of channels is very small and where it's actually a countable number. Right? This expression came from multiplying the velocity times the density of states. The density of states is a concept we use when we have a large number of states and we want to know how they're distributed. When we have a small number of states, we simply count the states. When we have a small number of states, we'll have a small number of channels, and we'll just have a discrete number that we can count. So here's a beautiful experiment that was done about 1990 that shows what can happen in a small nano device at low temperatures where the scattering is suppressed and the transmission is 1, the device behaves ballistically. This is a two-dimensional resistor, so electrons flow in this resistor. It is here's contact 1, here's contact 2. The length is very short enough that we can approximate the transmission by 1. Okay, the width of this is given by W. And the special feature about this experiment is that the width is electrically controlled by 2 metal plates that are known as Schottky barriers. By applying voltages to these Schottky barriers, we can electrically control the width of this resistor. And then we can plot current versus width. Intuitively, we expect that the wider we make it, the more current. And we would just think that the wider it becomes, where it's like we're adding resistors in parallel. Classically, we would think that the current would be proportional to the width. But when the experiment is done, what we find is that if we measure the conductance as a function of width, the conductance doesn't scale linearly with W. It goes up in discrete units. And the discrete units are in units of 2q squared over h. So here you can see when we have 1 channel, 2 channels, 3 channels, 4 channels. We're getting conductance coming in discrete units as we make the resistor a little wider, a little wider, a little wider. Each time we make it a little wider, we get 1 more channel, and we get 1 more quantum of conductance. So this is really a remarkable feature of current flow in nanoscales. Ohm's law has been known for a long time. It's really surprising that as late as 1990 we could discover that there are new things that we didn't understand about Ohm's law. So these are phenomena that take place under ballistic conditions in small semiconductor devices. Most of the semiconductor devices that we make common use of these days are larger and they operate in a more classical regime of operation. Our approach can treat that region as well. So let's say now that we have a very long and a very large cross-sectional device, a lot of channels, very long, so there's a lot of scattering, and let's ask if we can calculate the current in the plus x direction. Actually, we're going to think about our device as being a rectangular parallel pipette of semiconductor with some cross-sectional area A and some length that is many mean-free paths long. It makes more sense then to ask what is the current density, not what is the current, because the cross-sectional area A is arbitrary and can be scaled to anything we like. There's a minus sign here because I'm interested in the current in the plus x direction, and we have defined the current direction in this little nano device to be positive when it flows into contact 2, which is in the minus x direction. All right, so let's compute the current density with our approach. Here's our conductance expression, assuming small applied bias. Here's our transmission expression, but we have a device that is, or a semiconductor slab that is very long compared to a mean-free path, so it simplifies to the transmission in the diffusive limit. We're interested in the current density, which is current divided by cross-sectional area. When we do this calculation then, we will get a current that is given by this expression times voltage. But we recognize that where the voltage came from is the voltage was producing a difference in Fermi levels. So Fermi level 1 and Fermi level 2 are different. If I take the change in Fermi level and divide it by the length of the conductor, I'm really taking the gradient of the Fermi level. Okay, but I have to be a little bit careful here, and we're going to talk more about this several times as the course develops. Fermi level is a concept we introduced in equilibrium. It is defined in equilibrium only. But we're going to think there's a quantity that is analogous to the Fermi level out of equilibrium. That's what I mean by this F sub n. We'll call it the quasi-Fermi level. So QV divided by L is the gradient of the quasi-Fermi level. It's actually minus the gradient because a positive voltage lowers it. So this gives us our current expression. We put it all together. We lump all of these parameters into one unit that we call the conductivity. And then we have a slope of the quasi-Fermi potential, and we get a very important relation. Current is conductivity times the gradient of the quasi-Fermi level expressed in units of electron volts. And we have an expression that relates this conductivity to the material properties, to the scattering that goes on, to the number of channels in that semiconductor slab. So we have an expression. This is a current expression that is a traditional expression for bulk materials. It's probably 100 years old or so. We have derived it in a way that it's consistent with nanophysics as well, so that we have an approach that will take us to small scales when we need to, but that gives us the right answer when we're dealing with larger scale structures. So we've developed a very important result, a current equation for bulk semiconductors. The current is proportional to the conductivity. Frequently, we'll talk about resistivity, which has units of 1 over conductivity, and which we measure in ohm meters. In SI units, we'll usually quote it in ohm centimeters because semiconductor people prefer to do it that way. The important point to remember is that current is proportional to the gradient of this quantity we've introduced, which behaves like a Fermi level and which we call a quasi-Fermi level. Now, traditionally, semiconductor people like to treat this a little differently. They like to define the conductivity as being NQ mu. Now that makes some sense because you would think that more electrons give you more conductivity. The conductivity should depend on the charge on an electron as well. And the other constants of proportionality we lump together into a term that we call the mobility, which has the units of meters squared per volt second. And again, that's a proper SI unit. We will usually quote its numerical value in centimeters squared per volt second because that's the way semiconductor people like to do it. So when I use that definition for the conductivity, I can rewrite my current expression as N times mobility times gradient of the quasi-Fermi potential. So either one, either this approach or this approach are identical, and we could use either approach. Now, just a word or two about this quasi-Fermi level. And we will see more about this as we progress in this unit and in the next one. As I mentioned, it's analogous to the Fermi level, but it is defined out of equilibrium as well. It reduces to the Fermi level in equilibrium. This term quasi-Fermi level was introduced by William Shockley, one of the inventors of the first transistor. People in other fields, chemists and material scientists, might know this quantity as the electrochemical potential. So it is a well-defined potential that we will frequently make use of. Now, you'll recall that the Fermi level was used to relate the equilibrium carrier concentration to the location of the Fermi level with respect to the bottom of the conduction band. If I have electrons in a device under bias, I will be out of equilibrium. The way I would relate the electron concentration to the Fermi level is I'd have to introduce something like a Fermi level. I would put a quasi-Fermi level. So I would replace the Fermi level in my equilibrium expression with the quasi-Fermi level, and now I'm describing the electron density out of equilibrium, so I no longer have this subscript 0, which denotes equilibrium. Now, in equilibrium, we know that current can't flow. If the current flowed in equilibrium, we'd have a perpetual motion machine, and we know that can't be. So in equilibrium, the current flow will be 0. That means that the slope of the quasi-Fermi level must be 0, but the quasi-Fermi level reduces to the Fermi level in equilibrium, so that means that the Fermi level is constant, independent of position in equilibrium. That is a really important fact to remember. In equilibrium, the Fermi level is uniform, independent of position. We have been assuming that the temperature of the two contacts is the same, even if the temperature of the two contacts is different. In equilibrium, the temperature of the two contacts would not be different in equilibrium. So the Fermi level is independent of position in equilibrium, an important concept to remember. Now, let me say a little bit about this mobility. This will become this is a very important parameter when we're producing semiconductor devices. We generally seek materials that have a high mobility because that leads to large currents for small applied voltages. The mobility comes when we write the conductivity as NQ mu. You should remember that conductivity is really the fundamental quantity. Mobility is a derived quantity. We have an expression from the Landauer approach to compute the mobility for any material. If we want the mobility, we just define that conductivity to be NQ mu, and that tells us how to compute the mobility. So to evaluate the mobility, we should begin with the conductivity. This is the expression that we have developed for conductivity. Okay. Now, just to simplify things, let me assume that the mean free path is independent of energy so that I can pull it out of the integral. That makes sense for common semiconductors like silicon with acoustic phonon scattering. Let me assume that I have a 3D semiconductor with parabolic bands, so there's a simple expression for the number of channels. I know the Fermi function, so I can compute the derivative. You can put everything together and do the integral. Here's the result that you will get. All right, a little bit complicated, but it's just some straightforward algebra, calculus. You'll notice an exponential here. So that exponential is signaling that I have made an assumption of a non-degenerate semiconductor. More generally, if I do this integral, I'll get Fermi-Dirac integrals. But when I see that exponential, an exponential of EF minus EC over KT, it spurs my memory, and I remember that that exponential occurs elsewhere too. That occurs when relating the electron density to the Fermi level. What that means is that I could replace this exponential with an expression that involved the electron density, and I could rewrite my term for the conductivity. Well, just doing that algebra, this is what we find. The conductivity is N, Q, times a bunch of parameters. That collection of parameters we call the mobility. So that's our derivation of mobility. It is something with the units of velocity. times the energy independent mean free path divided by 2 kT over Q. The units are, as commonly used in semiconductor work, centimeters squared per volt second. What is this velocity? It just comes about from this algebra, but it turns out to have a physical interpretation as well. It is the thermal velocity. It increases as the square root of temperature. The velocity is slower for heavy effective masses. Physically, this is the velocity along one of the coordinate axes. This is the average velocity of all electrons that have a plus x velocity, for example, or a minus x velocity. They're the same. So this is the velocity along one of the coordinate axes. And finally, note that what comes out of this also is, if I take kT over Q times this mobility, we'll get thermal velocity times mean free path divided by 2. Earlier I had said that that quantity is the diffusion coefficient. So we have found from this little exercise that there is a relation between the mobility and the diffusion coefficient, and it's a very simple relation that simply involves kT over Q. We'll discuss that a little more later. Okay, so let's summarize. We have a general expression for computing the current in a two-terminal device. We can use that expression for small devices and describe phenomenon like quantized conduction. On the small devices, m is a small countable number, and if the device is short, the device is ballistic and the transmission is 1. Now, I can also use this same expression and let the length get large, let the device cross-section get large, so there are many channels, and we will get this classic expression for the current in a large semiconductor device. So the current is proportional to carrier density times mobility times the slope of the quasi-Fermi level, this quantity analogous to the Fermi level, but out of equilibrium. Okay, so we have covered a lot of ground. We are now going to focus on bulk transport, and we will show that this equation can be rewritten in another way that is very common and is frankly often the starting point for work in semiconductor devices. The name of that equation is the drift diffusion equation, and that's the subject of the next lecture.